Greetings to all. I am Dr. D. Devasena, Assistant Professor from the Department of Electronics and Instrumentation Engineering, Sri Ramakrishna Engineering College. Today, we have a brief discussion on Fast Fourier Transform. The Fast Fourier Transform and Discrete Fourier Transform are mathematical techniques used for analyzing the frequency content of signals. FFT is an algorithm used to compute DFT efficiently. The FFT is an algorithm used for computing DFT with reduced number of calculations. It is based on Cooley-Tukey algorithm with radix 2, in which an n-point sequence is decimated into 2-point sequence, and from the results of 2-point DFTs, 4-point DFTs are computed, and from the results of 4-point, 8-point DFTs are computed. Let us discuss few major advantages of FFT over DFT. The first one is computational efficiency. FFT is significantly faster than DFT since it uses symmetries and properties of the input signal to reduce the number of computation. The second major advantage of FFT is time complexity. To discuss time complexity, we will define the DFT definition by x of k is equal to summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi k n divided by n, where k varies from 0 to n minus 1. So this is the formula used to calculate the DFT. Here for each output x of k, for k varies from 0 to n minus 1, we need some complex multiplications and additions. So for each output, the number of complex additions is given by, for each input, the number of complex additions is given as n into n minus 1, and number of complex multiplications is given as n multiplications. So for one input we have n into n minus 1 additions and n multiplications. So if we have n is equal to 4, so the total number of complex multiplications is equal to 4 into n, which is equal to 4 into 4, which is equal to 16. So the total number of multiplications required for n is equal to 4 is 16, and the total number of additions required for n is equal to 4 is equal to n into n minus 1, which is 4 into 3, which is equal to 12. So it requires 16 multiplications and 12 additions when in DFT. But in FFT, since it is based on radix 2 algorithm, the number of n can be equated as 2 per k. So for n is equal to 4, it becomes 2 per 2, where k is equal to 2, which includes number of stages in FFT. So which represents the stages. So similarly, we need to find the butterfly operations required in each stage. So the butterfly operations required in each stage is calculated by n by 2, which is equal to 4 by 2, which is equal to 2 butterfly operations in each stage. Here for one butterfly operations, the number of multiplications required is 2. One at top and another one at the bottom. And number of additions required is also 2, one positive and one negative. So to calculate the total number of complex multiplications and additions, we are using the formula complex multiplication is equal to number of butterfly operation into number of complex multiplications into number of stages. So the number of butterfly operation is 2, the number of complex multiplication is 2, and number of stages required is equal to 2. which is equal to 8. So the complex number of multiplications required in FFT for n is equal to 4 is 8, and similarly the number of complex additions required in FFT is also 2 butterfly operations into number of complex additions is 2 and number of stages is equal to 2, which is equal to 8. So when compared to DFT, in FFT the total number of addition is also 8 and number of multiplication is also 8, whereas in DFT the total number of multiplication is equal to 16 and addition is equal to 2. Here the time complexity required for computation is reduced when we are going for FFT. For example, if we consider for n is equal to 8, the total number of complex multiplication in DFT multiplication is n into n, which is equal to 8 into 8, that is 64, and addition is n into n minus 1, which is equal to 8 into 7, 56. The same has been implemented when FFT. So here the n is equal to 8, which is equal to 2 power r, which is equal to 2 power 3, where r or k, whatever it may, we can represent r or k. So which is equal to 3 stages. So 3 stages, and number of butterfly operation is n by 2, which is equal to 8 by 2, which is equal to 4. So for one butterfly operation, the number of complex multiplication is equal to 2 and number of complex addition is equal to 2 for one butterfly operation. So total multiplication is, number of butterfly operation is 4 and number of additions, number of multiplication is 2 and stages is equal to 3. So which is equal to 24. And while calculating the total number of additions, the number of butterfly stages is equal to 4. The required number of additions for each stage is equal to 2. And the total number of stages for n is equal to 8 is equal to 3, which is equal to 24. So this proves the time complexity is reduced in FFT, because when we are having higher order n values, instead of using DFT, which has higher multiplications and additions, we can go for FFT, which has lower number of multiplications and additions when compared to DFT. As we discussed, the time complexity is reduced in FFT when compared to DFT. And the third major advantage is memory requirements. Since FFT algorithms are performed due to divide and conquer concept, less number of memory is required when compared to DFT. So finally, the cardboard implementation is also very advantageous, where real-time processing required is simple when compared to DFT. Let us start with the derivation of FFT in decimation in time domain. So decimation in time domain. Which is called as DIT algorithm. So here in decimation in time domain, here the radix to FFT algorithm converts the time domain n point sequence in x of n to n frequency domain n point sequence, which is called as x of k. In decimation in time algorithm, the time sequence x of n is decimated into smaller DFT and computation is performed. So the results of smaller DFTs are combined to produce the result of n point DFT. Here, for example, if n is equal to 8, it is divided into 4 and again it is divided into 2. So here it is called as n stage, this is called as n by 2 stage, and this is called as n by 4 stage. After computing all these three stages, we can get the results of n point DFT. So from basic n by 4 to n by 2 and from n by 2 to n stage can be computed. Let us consider x of n have n number of samples. Here we can decimate x of n into n by 2 samples. Here we are naming the n by 2 as f1 of n and f2 of n. So here the f1 of n is denoted as x of 2n, where n varies from 0 to n by 2 minus 1, and f2 of n is denoted as x of 2n plus 1, which is equal to 0 to n by 2 minus 1. So the 8 point, for example, if n is 8, the 8 samples are divided into 4 samples. The first 4 indicates the even samples and the second 4 indicates the odd samples. So if x of n is 8, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 up to x of 7. So there may be 1, 2, 3, 4, 5, 6, 7, 8 samples. In 8 samples, the f1 of n indicates the even samples present in the x of n. So which is x of 0, x of 2, x of 4 and x of 6. Similarly, the f2 of n indicates the odd samples present in the x of n, which is x of 1, x of 3, x of 5 and x of 7. So the f1 of n indicates the even components and f2 of n indicates the odd components. So if we are going for derivation, let x of k, we are denoting it as n point DFT. It is divided into 2 components. One is f1 of k, next one is f2 of k, which is called as n by 2 point DFT. So now we can derive the components. By using the formula, we know x of k is equal to summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi k n divided by n, where k varies from 0 to n minus 1. So here by considering e power minus j 2 pi k n by n as twiddle factor, it can be changed as Wn per Kn. This is called as twiddle factor, which is used to represent e power minus j 2 pi divided by n. By using this, we will establish the equation as x of k is equal to summation n is equal to 0 to n minus 1 x of n. The term e power minus j 2 pi k n divided by n can be written as Wn power k into n. Now we know that here the x of n is divided into f1 of n as we discussed earlier and f2 of n. Now I am writing this equation x of k is equal to summation n is equal to 0 to n by 2 minus 1. Since this f1 of n is n by 2 minus 1 component and f2 of n is n by 2, another n by 2 minus 1 component, I am changing the summation as n is equal to 0 to n by 2 minus 1 f1 of n into Wn power k into n plus summation n is equal to 0 to n by 2 minus 1 f2 of n into Wn power k into n. So we know that f1 of n as x of k is equal to summation n is equal to 0 to n by 2 minus 1. We can write f1 of n as x of 2n into Wn k. Instead of n, we will need to change it as 2 into n plus summation n is equal to 0 to n by 2 minus 1. This f2 of n can be written as x of 2n plus 1 into wn k into, instead of this n, we need to write it as 2n plus 1. So now we will go for the next step. So from the last equation, 0 to n by 2 minus 1 x of 2n w, I am bringing the upper n 2 in the bottom. So n by 2 k into n plus summation n is equal to 0 to n by 2 minus 1 x of 2n plus 1 into, here we are having two terms in the place of n, that is 2n plus 1. We are splitting this as wn k into 2n plus wn per k. Now it becomes summation, this term will be the same, n by 2 minus 1 x of 2n w n by 2 per k n plus, I am taking this with this term is without n, so I am taking this without n term as a constant and I am bringing it outside. So it becomes w n power k into summation n is equal to 0 to n by 2 minus 1 x of 2n plus 1 into w n by 2. This 2 becomes to the denominator, so it becomes k into n. So from this we can state this f of n is f1 of n and here it is f2 of n. So it both represents the formula for DFT. So this whole terms becomes f1 of k plus w n power k into f2 of k. So this is equal to my x of k. Now the 8-point DFT is split into 4-point DFT, one f1 of k and another 4-point DFT f2 of k, or my n-point DFT is split into n by 2-point DFT plus another n by 2-point DFT. Similarly, this f1 of k, we have to divide this f1 of k and f2 of k into further decimation. So if it is n point, we have divided this n point as 2 4 points. Again this 2 4 points should be divided as 2 points. So I am considering again my f1 of n. Now my f1 of n is equal to dividing into two components. One I am naming it as v11 of n. Another one I am naming it as v12 of n. So it is again represented as f1 of 2 into n. And this is f1 of 2n plus 1. As we have seen in our previous work, so we know that my f1 of n is equal to, this is derived in the past. So we know that f1 of n is equal to x of 0, x of 2, x of 4 and x of 6. So this represents my 0 place, this represents my 1 place, this represents my 2 place and this represents my 3 place. Again here this v11 of n is equal to f1 of 2n for n varies from 0 to n by 4 minus 1. So this is nothing but 0 to, if n is equal to 8, it is nothing but 8 by 4 minus 1, 2 minus 1, it is 1. So 0 to 1. So here again it is split into even component, that is the first component x of 0 and the second even component x of 4. And this v12 of n is equal to f1 of 2n plus 1, that is equal to odd components, which is nothing but one component which is x of 2 and the third component which is x of 6. So similarly, my f2 of n is also divided into v21 of n and v22 of n, which is equal to f2 of 2n and f2 of 2n plus 1. We know that f2 of n is equal to x of 1, x of 3, x of 5 and x of 7. This has been derived in the previous. So here it represents 1 position, 0 position, 1 position, 2 position and 3rd position. Here also, here n varies from 0 to n by 2 minus 1 and here the n varies from 0 to n by 4 minus 1. So this f2 of 2 of n is nothing but the even component which represents x of 1 and my x of 5. And this f2 of n represents the odd components which is x of 3 and x of 7. So now as discussed, one 8-point DFT is decimated into 4-point DFT, which is represented as f1 of n and f2 of n. So again these 4 points are divided into 2-point DFTs, which are represented as v11 of n and v12 of n, and again v2 of n and v22 of n. So now the input order has been changed as x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. Similarly, the output is also derived as per the procedures we have seen in the derivation of f1 of k and f2 of k. Likewise, the input has been reversed in decimation in time domain. So starting from the derivation, my x of k is n-point DFT and my f1 of k and f2 of k represents n by 2-point DFT and my v11 of k, v12 of k, v21 of k, v22 of k represents n by 4-point DFT. So if you are having an 8-point, it is splitted into 4-point DFTs and the 4-point is splitted into 2-point DFTs in the reversed input order of x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. So this is the reason why we are reversing the input in DIT algorithm. So based on this derivation, we will merge this as x of k is equal to f1 of k plus wn power k into f2 of k. Similarly, my f1 of k is the combination of v11 of k and v12 of k. So it represents v11 of k plus w n by 2 power k v12 of k. Similarly, my f2 of k is the combination of v21 of k and v22 of k. So it becomes v21 of k plus w n by 2 power k v22 of k. Here it represents 0 to n minus 1, Here it represents 0 to n by 2 minus 1, 0 to n by 2 minus 1. So for first x of k calculating, it includes the combination of f1 of k and f2 of k. 4 point. So both the combination gives 0 to n minus 1 value. The next f1 of k is the combination of v11 of k and v12 of k, which are 2 point and 2 point. So this 4 point is divided into 2 point and 2 point. So it ranges from 0 to n by 2 minus 1. Similarly, the f2 of k is the combination of v21 of k and v22 of k, which are 2 inputs, 2, which is the combination of 4. So the limits varies from 0 to n by 2 minus 1. So based on this, we will have a derivation how to draw the butterfly structure. F1 of k is equal to V11 of k. I will show a simple example for one derivation. So we know that this is the F1 of k. So I have to substitute the values from 0 to n by 2 minus 1. So if I am considering my n is equal to 8, it varies from 0 to 8 by 2 minus 1, which is equal to 0 to 3. So I am first substituting for k is equal to 0. So it becomes f1 of 0 is equal to v11 of 0 plus w n by 2 power 0 v12 of, I am substituting all the k values is equal to 0. Similarly, for k is equal to 1, it becomes f1 of 1 is equal to v11 of 1 plus w n by 2 per 1 v12 of 1. Similarly, for k is equal to 2, f1 of 2 is equal to v11 of 2 plus w n by 2 power 2 v12 of 2. So k is equal to 3. f1 of 3 is equal to v11 of 3 plus w n by 2 power 3 v12 of 3. So by using the symmetry property of DFT, we are equating w n by 2 power 0 is equal to w n by 2 power 2. So we can name it as, instead of w n by 2 power 2, we can change it as minus w n by 2 power 0. So here it becomes so the last two terms becomes v11 of 2 minus w n by 2 power 0 v12 of 2. Similarly, this can be written as v11 of 3. Instead of w n by 2 power 3, we can write as w minus w n by 2 power 1 v12 of 3. So from this we can conclude that for each outputs, there are 4 outputs, f1 of 0, f1 of 1, f1 of 2 and f1 of 3. From the 4 outputs, the first and the third outputs use the same Tudel factor with sign change, and the second and the third output uses the same Tudel factor with a sign change. So this shows how to draw the butterfly structure, basic butterfly structure. So in basic butterfly structure, if you are having 2 inputs, the first output is the addition of 2 inputs multiplied by the Tudel factor, and the second output is the subtraction of 2 inputs multiplied by the Tudel factor. So it becomes if you are having two inputs, for example V11 of 0, V12 of 0, the first one is V11 of 0 plus twiddle factor into the second input V12 of the 0, and the second output is V11 of 0 minus Wn by 2 power 0 V12 of 0. So the first term indicates the plus addition, the second component indicates the subtraction. So multiplied by the same twiddle factor. So I am indicating the twiddle factor in the lower end of the butterfly structure. So from this we are estimating the time complexity, that is it requires one complex multiplication in the top end and another complex multiplication in the bottom end with two complex addition, one is positive and another one is negative. So the totally one butterfly structure requires two complex multiplications and two complex additions. From this we are calculating the time complexities. So based on this the DFT the time consumed by the FFT is reduced, and also the derivation is used to solve the compute the DFT very efficiently and easily when compared to your normal direct computation of DFT. So finally we conclude this derivation. So based on this derivation we will solve some problems in the forthcoming sessions. Thank you.